Okay, where we've been at is we've been plotting through units. We want to describe and indicate how much radiation we received, how much radiation our patient received, and there's been such a confusion of units that have evolved over the years. When I first started, we were using milliroentgens, which was an expression of how many ionizations occur in air. Well, right there you can see a problem. Who cares about air? And so we went on to other units, and but the more important ones, we used the idea of Kerma, air Kerma. Air Kerma was telling us, well, how much kinetic energy is released in air. Again, we're still talking about air. So we were using either exposure measured in milliroentgens or air Kerma that that specified how much energy was released whenever you had ionization. But then we saw that we would like to know the dose to particular tissues. The dose was energy per unit mass, energy absorbed per unit mass. So we went on to dose given by grays and milligrays. Over in the old system of units, it was the rad and the millirad. But then we saw we had to take into account the different types of particles and the way that they deposited energy along their path. That was the LET measure. And using the LET measure, we came up with the effective dose, and not the effective dose, the equivalent dose, ED. And this is where we're at now. We saw that the equivalent dose is given in a millisieverts, sieverts and millisieverts. In the old system, it was given by rems and or millirems. But again, we emphasize the new units, the millisievert unit. And this is where we're at now. That successfully takes into account how to combine different radiations. Let's see what's going on here. And we gave this example to illustrate the use of equivalent dose. Here's an individual that received 3 different types of radiation. You just cannot add those milligrays from each of those radiations because those radiations have different expressions of radiation hazard. It depends on the LET. It depends on how the energy was deposited along the path. So you cannot just say, well, 10 plus 10 plus 10 gives me 30 milligrays. Yeah, you have to include the radiation weighting factor, which takes into account those LETs. The radiation weighting factor for X-rays was 1, so that gives you a total of 10 millisieverts. For electrons, it turns out to be also 1, another 10 millisieverts, but the slow neutrons have a much greater LET, 5 times more hazardous. So you have to multiply the dose 10 by 5, and now you got 50, which gives you a grand total of 50 millisieverts. So now we have successfully taken into account different types of radiation. Do you think we've arrived? Nope. We have a problem. That the bottom of that slide just tells you that you have to take into account the radiation weighting factor. And now we pick it up with new information. What's the problem with the equivalent dose? Well, what if I told you that I received 5 sieverts? What do you expect, the clinical expression of 5 sieverts would be? What would be the results of 5 sievert a dose? Well, a little bit of radiobiology. There's something called an LD50-60, lethal dose to 50% of the people that'll die in 60 days. Okay, and well, that's if you had a whole body dose. But what if you just had a dose for a particular tissue? See, that's the problem with the equivalent dose. It doesn't tell you which tissue got radiated. And for instance, if you're going into fluoroscopy and you're wearing a lead apron and a thyroid shield, you press the pedal. Now your hands get a certain amount of radiation, your facial area gets a certain amount of radiation, and the body organs get a certain amount of radiation, whatever was able to wiggle through that lead apron. There's always some a transmission through that lead apron. And so what we're going to do for the next step is we're going to be talking about risk. We're going to be looking directly at, well, the so what. I can tell you how much equivalent dose you got. That tells you how much absorbed dose you got, taking into account the LET. Those are all physical factors. But now the question arises, well, so what? What's my risk? What's going to happen to me as a result of that exposure? And this is where we're going to come in with a new concept, a concept that depends on risk. And to take into account the risk, you have to know which tissue got radiated, because each tissue has a different risk of developing a disease. Uh, uh, so it has to take in the sensitivity of the tissue. So, for instance, if I had just said a 5-sievert dose, well, you would think, well, that'll be 50-60, lethal dose to 50% of the people that'll die in 60 days. But what if you didn't have a whole body dose? Okay, what if it was just to a fingertip? Well, a fingertip, you're not going to die from a 5-sievert dose to a fingertip. While the LD50-60 was between 4 and 5, you're nowhere near a fatal dose as a result of a fingertip exposure. What will happen? What disease will you be at risk for? Well, you'll certainly get an erythema. Erythema responses are a threshold response. Typically, we state around 2 sieverts. So if you got 5 sieverts and the threshold is 2, you most certainly will come out with a little pink fingertip, like a sunburn reaction. But there's also another possibility. You can come down with a skin cancer, and here's a point to take home. All solid cancers take on the average between 20 and 25 years to develop post-exposure. 20 to 25 years. It doesn't happen overnight. And the only exception to that is the non-solid tumors. The leukemias only take 2 to 3 years. Take that home with you also. 2 to 3 years for leukemia, average latent period post-exposure, and 20 to 25 years post-exposure latent period for solid tumors. Well, what if it was 5 sieverts to the lens? Well, now you're at risk for a different disease, a cataract formation. Cataracts also, we state, is between 500 and 2 sieverts. The 2 sieverts is the official number today, but it's in the process of being changed down to 500 millisieverts. So again, you have to have an expression of risk, you have to know what tissue got radiated and how much it got radiated by. What if it was 5 sieverts to the gonads? Now we have a totally different risk with a totally different biological effect. See, now we're worried about sterility. 5 sieverts is right at the bottom, a threshold. Sterility effects are threshold effects also. 5 sieverts, typically we think more like 6 sieverts. So you're just about, for temporary sterility, you're just about right at the bottom of the possibility of kicking in a temporary sterility endpoint. You can also have, if you happen to be pregnant, malformations at 5 sieverts, so you can be pretty sure there's more likely to be malformations. How about genetic effects? Well, those are considered to be the least likely result of exposure at 5 sieverts, but those are possible as well. We'll be talking more about malformations, genetic effects, sterility effects, all of that when we get to the radiobiology factor. Here I just want to emphasize, you have to state dose and you have to state tissue. Each tissue has a different risk or different sensitivity. And then what if you have multiple tissues? I mentioned the fluoroscopy situation where you're not only getting exposed to the hands and to the face, you also get your visceral organs to some extent are also being exposed. What is the solution to all of this? What's the next level beyond ED, equivalent dose? It's the effective dose, effective dose. Be careful with the terminology. We were talking before about equivalent. Now we're talking about effective. But both of those are doses, okay? And this is the way we put it all together. The effective dose is defined as you identify a particular tissue given by the letter T. You get the equivalent dose to that tissue. Then you multiply by the tissue weighting factor. Hey, another weighting factor. For the equivalent dose, we use the radiation weighting factor. But now we have a tissue weighting factor, totally different factor. And once you get that for a particular tissue, then you do it for the other all the other tissues that got radiated, and you get the sum of all those individual products for all those individual tissues. Okay? That's the way we define effective dose. And what does this incorporate? It takes into account the average dose to each individual organ, and it takes into account the sensitivity of that organ. Now, here's an important point. Effective dose is stated only for stochastic risk. You're going to hear this word over and over again, stochastic. Stochastic implies probability functions, a probability effect. There's only two diseases that we classify as being stochastic, and those two are carcinogenesis and mutagenesis, cancer and genetic effects. Okay. In general, there's a dichotomy here. We're talking about stochastic effects, which are, as we just mentioned, carcinogenic and mutagenic. And the point to observe is no threshold, no threshold. In other words, there's a probability, there's that word probability, there's a stochastic effect no matter how low a dose you get. There is no threshold. There is no 0 point that we assume for stochastic effect. On the other hand, there's something called a deterministic effect. The deterministic effects do have a threshold, and they represent all the other effects. I've only mentioned a few: cataracts, erythema, temporary sterility, hair loss, congenital effects. All the other effects other than mutagenic or carcinogenic are considered deterministic. Okay? So coming back to the effective dose, it's going to take into account partial body doses. When you take a patient exam, isn't that a partial body? A chest film only covers the chest, et cetera, et cetera. So with this definition we just had, we can now take into account partial body radiation, which is our reality for personnel, and it's our reality for the patient. Okay, and where do we get these tissue sensitivity factors? From the Japanese A-bomb survivors, mainly. That's a very large population. We've been studying them since 1945, so that we have been able to account for the long latent periods of cancer. And you remember, 20 to 25 years for the solid cancers. And we can account for the genetic effects. We've got a number of generations now since 1945 that we can study. And again, we emphasize it's the effective dose is only for carcinogenic and genetic effects. Okay. How about the units? The units is going to be the sievert. 1 sievert is 1 joule per kilogram. Notice that the sievert is a unit of dose. It's an effective dose. Remember, dose was joules per kilogram. And the old system, it was the rem. And as we can still convert from sieverts, from rems to sieverts and back vice versa. 1 sievert is 100 rems. And again, I remind you of the equation defining the effective dose E. Up on top here, I've also placed the old designation. In the classical units. We were using what they call dose equivalent. To make a difference between the old classical units, dose equivalent, to the new set of units, we call it equivalent dose. We just flip the letters. Okay. And notice that the units for equivalent dose and effective dose is both joules per kilogram. Okay. It's still dose. Well, let's move on. I mentioned that we have to incorporate the tissue weighting factors. Here they are. Don't have to remember them, but what you see here is a relative risk table. Relative risk. For instance, let's take breast. It has a tissue factor of 0.12. Compare that with skin. It has a tissue factor of 0.01. Conclusion, breast is 12 times more sensitive to developing a carcinogenic or stochastic effect than skin. Okay? Likewise, we could say the same thing for a lung, colon, breast, and bone marrow. They are all 12 times, and stomach. They're all 12 times more sensitive than skin. How would you compare, let's say, bone marrow versus thyroid cancers? Well, notice 0.12 versus 0.04. The thyroid is 3 times less sensitive, or putting it the other way around, the bone marrow is 3 times more sensitive than the thyroid. Likewise, that's true for the breast, colon, lung, and stomach, and on and on. These are relative risk, and you can compare the risk of one disease versus another disease, but as we've seen, we can use this to add up your risk. If I added up all these numbers, they come out to unity, 1.0. Okay, and what that means is that if I come up with a certain risk of skin cancer, and then I get a risk of because in fluoroscopy I expose my hands, so I have a certain risk of skin cancer to my hands, but I also expose my thyroid. Certain amount of radiation gets through my thyroid shield, so I could figure out, well, how much a risk do I have of a thyroid cancer? How much risk do I have as of skin cancer? And what would be my total risk of coming down with any kind of cancer? It would be the sum of those two. Isn't that what that equation that we were using expresses down at the bottom of the slide, where the effective dose is a measure of risk, taking into account the sum of the individual risks. How did we get the individual risk? We got the dose to a tissue multiplied by the sensitivity of that tissue. Okay? So the total risk is the sum of the individual risks. Moving on. Here's an example for the thyroid, where the tissue weighting factor is 0.04. We just saw that it was 4 times more sensitive than skin, right? 0.04 versus skin of 0.01, factor of 4. Okay. Here's another example before we leave this. You have 20 milligrams to the skin. Let's assume that there was no other exposure. In fluoroscopy, you're going to have exposure to a number of other organs, but let's just identify just the skin, 20 milligrams. Find the effective dose. Well, it's 0.01, the tissue factor, multiplied by the 20, and you come up with 0.2 millisieverts. What does this mean? Take this interpretation home with you. Okay, you got a, in this case, a 0.2 millisievert dose. How do you interpret these doses? Okay, the way you interpret it is, if you got 20 milligrams to the skin, you would run the risk of as if you would, that would be the same as a risk if you had gotten 0.2 sieverts, millisieverts, that's the effective dose, to the whole body. Okay, in other words, 20 milligrams to the skin is the same as 0.2 millisieverts to the whole body, in that it will give you the same risk of a cancer. Okay, I'll repeat and then we'll move on. The dose to any particular tissue, or better still, the dose to any combination of tissues, when you express it in terms of effective dose, will give you the risk to the whole body. It's as if you had radiated the whole body to that effective dose. Okay? And then you'll have the same risk that you would have had to any one of those individual organs that were into that calculation. It's just the sum of all the risks, and it comes out to 0.2 millisieverts in our example, where only one tissue, the skin, was exposed. Now, in practice, you really don't have a good handle on how much dose your liver got, your stomach got, your colon got, your breast got, all these individual organ discs. I just want to mention that we do have a little shortcut that you can use to make a calculation based on your badges, this comes from computer modeling, but it's kind of interesting. You get a reading on your badge. From the reading on the badge and making certain assumptions of the transmission through the apron and et cetera, et cetera, this is what you come up with. If you have 1 decimeter, if you take 1/3 of that reading, that would be your effective dose. Okay, these are called the Webster rules. If you have 2 decimeters, most people have 2 decimeters these days. I don't know what your group has, but if you have 2 decimeters, there's a little equation that you can use that will also come up with the expression of how much dose, what's your effective dose from a combination of those 2 decimeters, 1 decimeter outside the apron and collar level and 1 inside at the waist level. Now, do realize that there are limitations to this effective dose. One of the limitations is based on the use of the tissue weighting factor. The tissue weighting factor is an average of both genders. We know that genders, male, female, responses are different for many carcinogenic and mutagenic diseases. We know that there's a big difference in ages between children and older people, but yet that tissue weighting factor is an average of over all ages. So we have to be very careful with this effective dose. There's the atom bomb survivor data is subject to problems, dosimetry models. How do you know how much radiation a particular household member got 1 mile away from ground zero? They weren't wearing badges and dosimeters. We have to make estimates based on how was the wind blowing, how was the temperatures, temperature inversions, how much rain, what was the combination of particles within the exposure. We just saw that neutrons have a totally different biological effect than gamma rays and X-rays. So it's subject to technical extrapolations and assumptions that we have to make. There's another limitation. The atom bomb survivors were exposed at high doses and high dose rates. That's not true at the doses that you get, and that's not true at the doses that the patients get. Okay, these are high doses. There's no good reliable data below 100 millisieverts. But that's where we are exposed at, and that's where our patients are exposed at. So there's an obvious a disconnect. There's population differences. Remember, this was in the middle of a war, and the individuals were malnourished, poor medical health, ethnic differences, and cancer incidence. So here's a recommendation. After all this discussion on effective dose, we really don't want to use it for individual doses. Yes, you can use your Webster rule to find out how much you got, but that doesn't, you don't interpret it as what you really got. You can use that as a comparator. And this is where this effective dose is shines through for. You use it as a comparator. You have a particular protocol, and then you define another protocol. You get the effective dose of your patient, for instance, from using one protocol versus another protocol. And you get the effective dose from those various protocols. Now you can compare. You haven't looked at a particular patient. You've just looked at a generic protocol, and you can say, hey, using this protocol, I end up with less risk to my patient. Likewise, you can figure out from any particular procedure what your effective dose is, and then compare it with other procedures and come up to a comparative measure. Hey, if I do it this way, I get this effective dose. If I do it that way, I get this other one. Hey, I'm going to do it the other way because it's going to get less effective dose. It's for comparison purposes, and you can't say, well, this is my absolute risk, period. It's more better for comparisons. Okay, here's we're now pretty much toward the end of this chapter. It's been a long haul for units. Here's a summary, bringing everything back into perspective. We started out with outputs from an X-ray tube measured with either exposure in milli-R or milligrays for air Kerma, and we measure either of those with ionization chambers. We went on to dose. How do we get dose? We multiplied the exposure by the F factor, and that gave us the dose. Then we multiply the dose by the radiation weighting factor to give us equivalent dose. That's the one that takes into account the LET, the way energy is deposited along the path. And now what we just finished looking at, the effective dose, which we now take into account the tissue weighting factor. Okay, the conversion factors was the F factor that depends on energy and atomic number. That's a very common question on the boards. What does the F factor do? It converts your exposure to a dose in tissue, exposure in air to a dose in tissue, and what does it depend on? Depends on energy and atomic number. Those two questions have asked over and over again. F factor converts ionization to dose to a particular tissue, and it depends on energy and atomic number. Radiation weighting factor converts the rads to sieverts. It converts the rads to rems, or the grays to sieverts. And the tissue weighting factor converts the dose equivalent, or the equivalent dose, to effective dose, which expresses risk of disease. And then what are the measures you need? For the air Kerma, ionization. For the dose, now here's a new idea. Dose is energy absorbed per unit mass. That means it's a measure of how much energy is deposited, and energy deposited in any system goes to raising the temperature of that system. So an absolute measure of dose would require calorimetry, and in our case, microcalorimetry. So by rights, those F factors should come from calorimetry, where we can convert ionization over to a dose. And but microcalorimetry is very, very finicky. You can deliver a lethal dose to an individual, and the temperature rise would be minuscule. So you're really looking at microcalorimetry, which we never do. Or at least we let the National Bureau of Standards and the national laboratories do it, and then they feed us the conversion factors, those F factors that we were working with. The equivalent dose, what do you need to know? You have to go to the biological effects of different ways, different radiations on how they deposit a dose. You got to get the LET. And we'll look at that much deeper when we get to radiobiology. And then finally, the effective dose. How do we get the effective dose? From known risk factors. We have to correlate how much did people get of dose and what were the chances of them coming down with a disease. That's how you get risk. And that's where we get mainly that A-bomb survivor population to provide those risk data. Well, that's the end of that. Let me I'll pick out for you a oops, wrong one. Go on to chapter 3. Chapter 3, I promise, is a little bit more exciting than units, and so I'm glad to get to chapter 3 before the day is over. Okay, here we go. What are we going to do in chapter 3? We're going to look at X-ray production. How do we get X-rays? You press on that pedal in fluoroscopy and boom, you see an image. Well, it's a long process between stepping on a process and looking at an image, but let's start that process. What's going on with the X-ray tube? What does an X-ray tube look like? What is it about an X-ray tube that will provide for the production of X-rays? There are two basic components of an X-ray tube. There's a cathode and there's an anode. The cathode, the business end of the cathode is a filament. That filament is a little coil of wire, helical spring-like coil of wire. It's made up of thoriated tungsten. And over on the other side, you have at the anode the target. The business end of the anode is the target. The target is typically tungsten for CT, radiography, and fluoroscopy, and molybdenum and rhodium for molybdenum type procedures. The X-ray tube is typically enclosed in a glass envelope, as shown over here. Inside that glass envelope, we have a vacuum, a very tight vacuum. And I'll indicate presently why we want a vacuum. But the step toward X-ray production is the following. Step number 1, you place a voltage across the filament. Remember what a voltage was? A voltage is a region of positive charge with an opposing region of negative charge. And here you're going to place that voltage across the filament, across this wire. So what's going to happen next? Well, what will happen is that the electrons inside the wire will be induced to move. And they'll move from the negative region. They're going to be repelled by the negative pole, and they'll move through the wire, through the coil, and through that filament to the positive side of that polarity. Okay, no X-rays yet, but now you've got current flow through the filament. By current, we mean the flow of electrons per unit time. The flow of electrons per unit time, and that's what you're going to get through the filament. Okay. Now, what happens when you have a flow of electrons pushing through a very thin wire? The filament is going to heat up. It's going to get hot. And what happens when filament gets, any filament gets hot? Well, if you toasted your bagel this morning, if you look inside your toaster, well, what do you see? You see a filament. And except that filament is relatively thick, and but it's the same principle. Pass electrons by turning that toaster on, pass electrons through that filament, the filament gets hot, and what will happen is that as a result of that metal getting hot, out comes heat. Right? And that heat is going to toast your bagel. How about your hair blower? Same thing. If you were to open up a hair blower, you'd find a big filament, and but you also find a little fan, so that as the filament gets hot, you blow the air out and you have a hair blower. How about a space heater? Again, a filament getting hot, you emit heat. How about a incandescent bulb? It also has a little filament. You pass a current through that little filament, and now something else happens. It gets hot, but most of the energy goes into or at least some of that energy goes into the production of light. See, hot filaments can emit light. Hot filaments can emit heat. But what does it emit in an X-ray tube? You emit electrons. Electrons. The material that you chose for the filament, that thoriated tungsten, had the propensity to emit electrons when it gets hot. And those electrons accumulate around that filament, and we say that you have produced an electron cloud. Sometimes also called a space charge, okay? No X-rays yet, but we're almost there, okay? And let's define some units. I mentioned electron cloud with charge. That's the unit of charge is the coulomb. The coulomb represents a certain number of electrons. Notice it's a huge number, 10 to the 18th, but also notice you don't have to remember that number, other than the fact that it's a large number. Then I mentioned current flow, electric current. Whenever electrons move, you have electric current. It's the flow of electrons per unit time, or another way of saying it is the flow of charge per unit time. And what's the unit of that? The ampere, abbreviated the amp. 1 amp is 1 coulomb, that's the charge, per second. It's a flow of charge per unit time here in seconds. We make many times an expression that you're boiling off electrons off of the filament. This thermionic emission that is occurring. First of all, look at the words thermionic emission. The ions are the electrons, negative electrons, and what this says is that you have the emission of negative electrons because of thermal heating by thermal means. And it's very similar to boiling off electrons from the filament. This idea of boiling off comes from its similarity to boiling water. Let's look at the boiling water because it's a perfect example of what's going on in that filament and the production of thermionic emission. Here's a pot of water. You heat it. The water, H2O, the molecules of water get kinetic energy. And as you can continue heating, the result of that kinetic energy is at one point, those molecules have sufficient energy to overcome the surface tension, the surface forces, and they go from the liquid phase into the water phase. Very familiar to you. And as your heating continues, you get more and more concentration of the vapor phase. The vapor phase is the equivalent to our electron cloud. What's going on is, in the case of the filament, the metallic filament, is that as it gets hot, the molecules, the electrons within the wire have enough energy that they overcome the surface tensions and the surface forces of that filament, and they go into the equivalent of the vapor phase. Okay. Now, what if you want more water vapor? Or in our case, what if you want more electrons? Many times we do want more electrons. Well, how do you get more water vapor? You increase the heat. Okay. In the case of the filament, the way you get more electrons in the cloud is you increase the filament current. You make the filament hotter and a greater temperature. And the greater the temperature of the filament, the more electrons are emitted. And by the way, how do you get more filament current? You have to increase the filament voltage. Okay? Now, how do we get the X-rays? We see that we have the electron cloud. Oh, this is step number 2. I think this would be step number 3, right? Let me check myself here. Oh, yeah, that's step number 1. Okay. I'm okay. It is step number 2. You place a voltage across the tube, and now you have a tube voltage. Don't confuse a tube voltage with a filament voltage. Notice we got 2 voltages here. One across the filament at the cathode and one across the tube. The one that we always talk about in practice is the tube voltage. The tube voltage. The engineers worry about the filament voltage. I just mentioned the filament voltage to set in motion a filament current to set in motion the thermionic emission, and now we have the more important idea: place a tube voltage. That tube voltage will attract the electrons that were just sitting in the cloud. Now they get to move. And in fact, because of that voltage, they are accelerated. And if they're accelerated, they get more velocity, they get more kinetic energy. And those electrons, when they impact the target, that kinetic energy is converted to X-ray energy as well as heat at the target. You have just accomplished the mission. X-rays are produced. And again, where did those X-rays come from? They came from the conversion of that kinetic energy that the electrons were arriving at the target with, the conversion of that kinetic energy over to X-ray energy. Unfortunately, you also have a lot of heat produced at the target. Heat that, if you don't control, can lead to the explosion of the tube, okay, which we obviously don't want to happen. Here's a little expression on where that energy is distributed. Kinetic energy goes both into heat and X-rays. And notice the difference. Notice the tremendous difference. Most of the kinetic energy delivered to the target appears as heat at the target. Only 0.5% is going to be useful X-ray energy. That's what keeps us in business, that 0.5%. All this other percentage is going to go into heat, which, if we don't control, will mean that you'll damage the tube. And these tubes are in the, all tubes are above $50,000. CT tubes more like over $100,000. If this is your private practice, you don't like to hear that your X-ray tubes are blowing up. So we're going to have to look at both of those effects. How do you get the X-rays, and what do you do with the heat? But let's continue our discussion. Remember, we saw that electrons are being accelerated to the target. Here's another little feature of the X-ray tube. There is a structure within the X-ray tube which we call the focusing cup. The role of the focusing cup is to to focus the electrons. Remember, electrons coming off of the filament are going in every which direction. They're not just directed toward the target. They go in, they're isotropically produced. They are produced in all directions, and you want to gather as many of those as possible and concentrate as many of those electrons as possible into a small spot on the target. Why a small spot? Because the smaller the spot, the better the spatial resolution image quality of the eventual image that you will form. Why that should be so? We're going to be looking at that in a subsequent chapter. But now do take home the idea that resolution improves as the focal spot size decreases. Okay? Here's some pictures showing you what we have. And there's that glass envelope I mentioned. There is the filaments in this enclosure. You don't see it too well. Later on, we're going to be talking about the anodes are not stationary. They're typically in radiology rotating. Why rotating? We'll look at that toward the end of this chapter. But there's your target. There's the source of electrons. The electrons will go across the space over here. And now we can say why you wanted why you wanted a vacuum in here. Remember that electrons are going across, and you don't want those electrons to waste their energy interacting with air molecules. You want to conserve that energy and deliver as many of those electrons with as much of energy as they have to the target. You don't want them to just use up their energy interacting in air. So that's why you have a vacuum. Here's a closer view of the filaments. All of our X-ray tubes have a small filament and a large filament. That's what they look like. And you can see that it's like a little coil there, and they're embedded in a little valley here, in a little indent, plus the structure that you see laterally to the filaments is your focusing cup. Nothing very fancy. It's just a little valley within which these filaments are, and again, the reason for the focusing cup was to get as many electrons into a smaller spot as possible at the target. And what is the role of having both a small and a large focal spot? Remember, the smaller you are, the better the resolution. Okay? We're going to be discussing the use of small and large focal spots presently. They are related to the heat dissipation mechanisms. Large focal spots will spread the electrons over a larger area of the target, and therefore spread the energy being delivered to the target over more metal within the target. Okay? Oh, that's going to require more discussion, which we will have. Here is some numbers that you should take home. They've asked many times on boards, what is the typical sizes of your focal spots for the mammal? They rarely, if ever, ask radiography focal spot sizes, but they're enamored with mammography, and mammography notice 0.1 millimeters for the small focal spot. Now that's small. You can hardly see a tenth of a millimeter. Okay, and compare that with the sizes of radiography. The take-home message here is, number one, remember the numbers for the mammal, and number two, remember that they are much smaller than radiography, right? 0.1 versus 0.6 for the small, for instance. Okay, let's go up beyond the X-ray tube. Oops, look at the time. The next step was to incorporate the tube housing over here, given with this red enclosure. When you walk into a room and you look at the X-ray tube, you don't actually see the glass envelope. You never see the glass envelope. What you see is the metal housing within which the X-ray tube is placed or inserted. Okay, and notice that there's an oil bath completely around the X-ray tube. And that oil bath is going to be for heat dissipation mechanisms. But at this point, I better let me finish this slide. Oops, yeah. The oil bath will have those two functions: the heat dissipation function. The oil has a very high specific heat, which means that it absorbs a lot of heat without rising in temperature. Well, if it doesn't rise in temperature, that means it keeps a good temperature differential between the target and the oil around the tube. So it's a very good mechanism of transferring heat away from the target to the oil. Okay. It also has electrical insulation. It has to protect against the possibility of electrocution. We're dealing with very high voltages, so that you don't want to electrocute yourself or your patient. Hey, we better stop at that point. Are there any questions before I bid you a good day? Okay, very good. You all have a good day.